prove that the tangents at the extremities of a focal chord on the parabola x squared equals 4ay intersect at right angles on the directrix. So here I have a focal chord. It's a chord that passes through the focus. Let's call the point here P, 2AP, AP squared, and then let this point be Q, 2AQ, AQ squared. And let's call the point at which they intersect on the directrix, hopefully on the directrix, that's what we have to show that this point is equal, let's call this point rather T, and we need to show that T is on the directrix and that this angle in here is 90 degrees. Okay, so first let's get the coordinates of T. So again, the equation of the tangent has already been proved in a previous video. If this question came in an exam and you weren't given, it didn't specifically say that the equation of the tangent is such and such, then you'll need to derive that from first principles. But since this is just a video on YouTube, for educational purposes, I'm just going to quote the equation of the tangent. So, the equation of the tangent at P is y equals px minus ap squared, and similarly at Q, it's qx minus aq squared. If you're not confident with that, go back and have a look at the video. So let's call this 1 and 2. Now I want to find the point T. T is where these two lines intersect, so I need to solve them simultaneously. So substituting 1 into 2 gives me px minus ap squared equals qx minus aq squared. Bringing the qx over here, and then at the same time factoring out x will give me p minus q multiplied by x, and bringing the ap squared over to this side, and at the same time I can factor out an a. I'll be left with p squared minus q squared, and then I can factor this as p minus q, p plus q, and I will cancel a p minus q with a p minus q, and so x is a into p plus q. So that's my x coordinate. Now what about my y coordinate? Well, I substitute this into either 1 or 2. It doesn't matter, I'll get the same answer. So a into p plus q, let's just sub it into equation 1. So that means y equals p multiplied by a into p plus q minus ap squared. A times p squared plus apq minus ap squared. ap squared and ap squared here go, and I'm left with apq. And so my point T has the following coordinates: a into p plus q, comma, apq. Now, does this prove that it lies on the directrix? Not quite. But we do have more information. We know that this chord passes through the focus because it's a focal chord. So, what am I going to say? Now again, I'm going to quote the equation of this chord. If you're not confident, go back and have a look at the video. So equation of chord PQ, what's that? That's y equals a half p plus q x minus apq. If this question came in an exam, you'd have to derive that because we're not given it the same with the tangents. Okay, now since this is a focal chord, I need to substitute these. I need to substitute the value of s into here because it should satisfy this equation. So, since PQ is a focal chord, I'm going to say s 0, a gets substituted in, and I have a equals 1/2 p plus q multiplied by 0. So in fact, this whole term is 0. Minus apq, I can say that that's all 0. Now if I divide by a, I'll have 1 equals negative pq, which is the same as pq equals -1. Okay, so what does this tell us? If PQ is -1, I can substitute this back into T because I have a PQ here. And so this means that T has coordinates A into P plus Q, comma, -A. -A, well, that's the y coordinate. So the y coordinate is always equal to -A, regardless of the value of the parameters P and Q, little p and little q, regardless what they are, this is always -A. And so that means that this point T will always be on this directrix, no matter which focal chord I take. So I could shift this focal chord around like this. It wouldn't matter as long as it's passing through the focus. I could shift it around, and the tangents will always intersect on the directrix. So this means that tangents intersect on directrix. But that's not the whole question. I also need to show that they intersect at right angles on the directrix. Well, let's have a look. From 1 and from 2, I can see that the gradient of the tangent at P is given by little p, and the gradient of the tangent Q is given by little q. Right, this is just the standard form. Y equals mx plus b. Y is mx plus b. And so my m here is equal to b and p and q, respectively, for tangents at p and q. So I can say that from 1 and 2, tangents at P and Q have gradients of little p and little q respectively. So that means that the gradient of the tangent at P equals P, and the gradient of the tangent at Q equals little q. Now I see what the question's given me. I need to prove that these are right angles. So what does it mean for two lines to intersect at right angles? It means that their gradients, when I multiply them together, give me -1. And so I can say that MP multiplied by MQ, which is P times Q, is equal to what? Is equal to -1, because that's the condition. This here is really the key in this question. This is the condition that makes this property hold, that the tangents at the ends of a focal chord intersect at right angles on the directrix. So it's equal to -1, which means that, last bit, which means that tangents intersect at right angles. Right angles. Okay, we're lazy. All right, right angles. And that's the end of the question, because I've shown that, where is it? They intersect on a directrix, on the directrix, and here they intersect at right angles.